So for a long time, interacting with artificial intelligence felt, well, a lot like consulting a highly detailed traditional paper map.
Right, yeah, like a static snapshot.
Exactly.
Yeah.
You look at it, you get your directions, and you set off. It gives you incredible information based on its, static view of the world,
Yeah.
but it doesn't actually know where you are.
No, not at all.
It doesn't know your vehicle's condition, and it certainly doesn't care if a massive roadblock just popped up a mile ahead of you.
It's essentially an isolated retrieval tool. I mean, it possesses a vast amount of compressed knowledge, but it has absolutely zero situational awareness.
Right.
And more importantly, zero capacity to act on your changing circumstances.
And that static paradigm is exactly what we're stepping out of today. We are moving way past the era of systems that just simply predict the next word in a sequence.
Yeah, that era is ending.
It really is. We're entering an era where AI operates more like a fully autonomous vehicle. Like it doesn't just reroute you when there's traffic. It drives the car, it books the hotel for your destination, and it, I don't know, negotiates the room rate while you're taking a nap in the back seat.
Which is a massive leap.
A huge leap. And that leap from a static map to an autonomous driver is what Antonio Gulli calls Agentic AI in his exhaustive new text. It's called Agentic Design Patterns, a hands-on guide to building intelligent systems.
And it is exhaustive. 424 pages.
It's a brick. But today, our mission for this deep dive is to basically rip the hood off that autonomous car. We're going to unpack the actual architectural blueprints, the design patterns that make these systems possible, and figure out what this fundamental shift means for, well, the future of work for all of you listening.
And to do that, we really need to strip away the marketing jargon first. We have to define what technically separates an agent from a standard language model.
Right, because everyone just says agent now.
Exactly. It's become a buzzword. But it is not just about parameter count or, having a larger neural network. It's fundamentally about an active cyclical behavioral loop.
Right. And looking at Gulli's foundational breakdown in the source material, it seems the real differentiator isn't how the AI generates text, but how it observes and iterates on that text.
Yes, the observation part is key.
So the text outlines this 5-step problem-solving loop. Basically, step 1, it receives a high-level mission from the user. Step 2, it scans the environment to gather context, so checking your calendar, reading your inbox. Step 3, it thinks it through and synthesizes that data to formulate a plan.
Right.
Step 4, it actually takes action. It executes the plan via software tools. And then, crucially, the 5th step, it learns. It monitors the outcome of that action, learns from any failures, and adjusts its future strategy.
That 5th step right there, that is the dividing line.
Learning from the failure.
Exactly. A traditional model generates an output, and its job is done. It just stops, regardless of whether that output actually solved your problem. But an agentic system evaluates the impact of its own action.
So it checks its own work.
Yeah. Like if it tries to send a calendar invite and the API rejects it because of, say, a formatting error, the agent observes that failure state, it rewrites the payload, and tries again.
Oh, wow.
And it does all of this without requiring you to prompt it a second time.
Which means we are essentially moving from a stateless query response dynamic to stateful, goal-oriented execution.
Stateful is the perfect word for it.
Right. And the text maps this evolution on a spectrum from level 0 to level 3. Now, if you've been following AI at all, you know that a standard base model level 0 is incredibly capable at reasoning, but it's tracked behind its training data cutoff.
Yeah, it's stateless, probabilistic text generation. Level 0 is just the core reasoning engine operating in a total vacuum.
Just a brain in a jar.
Exactly. Then level 1 introduces basic tool connectivity, giving that brain access to, say, a live search API. Level 2 brings in multi-step reasoning and strategic context management. But level 3...
This is where it gets crazy.
It really does. Level 3 is where the architecture radically changes. This is the implementation of collaborative multi-agent systems.
A multi-agent.
Right. You are no longer building a single monolithic AI program. You are orchestrating an entire ecosystem of specialized narrow agents working together to solve a larger objective.
It's like hiring an entire corporate department instead of a single generalist.
That's a great way to put it.
Like you instantiate a central project manager agent that delegates tasks to a specialized data extraction agent. And then that one hands data off to a specialized formatting agent. They just pass states back and forth.
They do. And as Marco Argenti highlights in the foreword of this book, shifting to this level 3 architecture fundamentally changes our relationship with the machine. Well, we stop telling computers what to do step by step, and we start declaring why we need something done, trusting the system to autonomously figure out the how.
But delegating the how introduces a massive, massive systemic risk, doesn't it?
Oh, absolutely. The stakes scale exponentially with autonomy.
Right.
Argenti makes a very sharp observation here. He says, look, if a level 0 system hallucinates while generating a recipe for, I don't know, a chicken salmon fusion pie.
Gross, but yeah.
Right. It's a harmless, funny quirk of text generation. You just laugh and write a new prompt. But if a level 3 autonomous system hallucinates while executing a complex algorithmic financial trade, or, while migrating sensitive client databases across cloud servers,
Then you're in real trouble.
catastrophic trouble. Plausible, confident garbage from an autonomous agent can permanently poison an enterprise ecosystem.
Which means if the stakes for autonomous execution are that high, we obviously can't just hand a language model a massive zero-shot directive and hope for the best.
No, you absolutely cannot.
Because usually if you throw a giant multi-part task at a model, it just results in severe instruction neglect. Like it focuses on the first thing you said and the last thing you said and completely drops all the constraints in the middle.
Yeah, the attention mechanism just break it down.
Exactly. Now, the text dedicates a lot of time to context engineering as the solution here, but I have to push back a little bit on this.
Okay, let's hear it.
Isn't context engineering just a dressed-up industry buzzword for writing a really long, overly detailed prompt?
I get why you'd think that. It's a very common misconception, but they are mechanically distinct.
Okay, how?
Well, writing a long monolithic prompt is exactly what causes the cognitive overload and instruction neglect you just mentioned.
Right.
The model's attention mechanism gets diluted across thousands of tokens. So, to prevent that, developers utilize a foundational pattern called prompt chaining.
Okay, let's unpack chaining.
Yeah.
This is basically the divide and conquer pipeline, right?
Correct. Instead of asking for everything at once, you build a sequential pipeline of discrete nodes.
Nodes. Got it.
So node A only extracts financial figures from a document. That's all it does. Node B takes the output of node A and summarizes the trends. Then node C takes the output of node B and structures it into a JSON payload.
So the model is only ever focused on one narrow, highly constrained task at a time.
Exactly. That is prompt chaining. Context engineering, however, is entirely different. It's about curating the state space before the model ever begins generating tokens.
Okay, so it's about building the informational environment the AI lives in.
Yes, it is the systematic integration of retrieval augmented generation. So, pulling exact factual documents from a vector database, along with real-time API outputs and the user's historical state.
Okay.
Context engineering treats the context window, not the model's internal neural weights, as the primary lever for accuracy.
Wait, say that again. That's important.
You are mathematically ensuring the model doesn't have to guess or rely on its pre-trained memory, because the exact verified truth is explicitly provided right there in its immediate working memory.
That makes total sense. Yeah, and that solves the hallucination and memory issues. But chaining forces the architecture into a very rigid sequential pipeline.
It does. It's a straight line.
Right. And if I'm building an agentic system to handle unpredictable customer interactions, say processing a routine return in one breath and then escalating a critical cybersecurity vulnerability in the next, a straight line completely breaks down.
Completely.
So how do we give these systems the ability to pivot dynamically without hard-coding a million different chains?
That requires moving beyond linear pipelines and implementing the routing pattern.
Routing?
Yeah, routing introduces a semantic decision-making layer at the very front of the architecture. When a user input arrives, a dedicated router agent analyzes the semantic intent of the request.
So it's not actually answering the user yet?
No, it doesn't generate a response at all. It acts as a traffic controller. If the intent is order status, it routes the payload down the logistics chain. If the intent is password reset, it routes to the authentication tools.
It functions exactly like an expediter standing at the front of a busy restaurant kitchen.
Oh, that's a good analogy.
Right. Like, they read the incoming ticket, they don't actually cook the food themselves, but they shout the specific orders to the grill station or the salad station. They manage the flow of control to the specialized workers.
That is a highly accurate way to visualize it. And if we stick with that kitchen analogy, it perfectly illustrates the next major design pattern too. Parallelization.
Because the sous chef on the grill and the chef on the salad station aren't waiting for each other.
Exactly. They are working concurrently.
Right.
If an agent needs to research the quarterly earnings of 3 different competitors, a sequential chain would search company A, wait for the network response, summarize it, and then start searching company B.
Which would take forever.
The latency makes it completely unusable for real-time applications. So, the parallelization pattern allows the agent to spin up 3 independent threads simultaneously. It fires off the data gathering tasks concurrently, waits for all of them to resolve, and then funnels that independent data into a final synthesis node.
But wait. If an agent runs multiple independent data gathering tasks concurrently, how does it synthesize conflicting information when those parallel tracks finally converge?
That's the trick.
Because if thread A says the stock is up and thread B finds an article saying it crashed, doesn't parallelization just create a massive collision of context at the end?
That is the crucial role of the synthesis node, which is often implemented as a MapReduce operation.
MapReduce, right.
The individual parallel threads, the map phase, only gather and format the raw data. They don't analyze it. The final node, the reduce phase, is given a specific system instruction to evaluate discrepancies. It weighs the recency or authority of the sources and explicitly highlights the conflict to the user rather than just blindly merging them together.
Okay, here's where it gets really interesting, though. If we have sub-agents running parallel operations and routing logic flying around in literally milliseconds, the risk of compounding errors seems massive.
It's a huge concern.
Because if the routing agent misclassifies a task, or a parallel thread pulls bad data, and the system is moving at computational speed, a small hallucination early in the flow just gets magnified tenfold.
Yes, it snowballs.
So how do these systems catch their own mechanical errors before handing a deeply flawed result back to the user?
They rely on metacognition. And specifically, this is implemented through the reflection pattern.
Reflection.
Right. This is a built-in architectural loop for self-correction. The system does not just produce an output and pass it to the user. It evaluates its own intermediate work against a set of constraints, identifies its own flaws, and then iteratively refines the response.
Okay, I understand the theory, but mechanically, I'm highly skeptical of this.
Let me guess, grading its own homework.
Exactly. If we are using the exact same underlying foundational model to grade its own homework, aren't we just baking its own internal blind spots into the evaluation? I mean, human beings are terrible at objectively proofreading their own writing. Why wouldn't a language model just rubber stamp its own output?
That is the exact vulnerability that naive self-reflection suffers from. You're completely right. To bypass that, developers use the producer-critic model within the reflection pattern.
Producer-critic.
You do not ask the same agent to write the code and evaluate the code. You instantiate 2 distinct, strictly prompted personas.
So you enforce a hard separation of concerns.
Exactly. The producer agent is prompted solely to generate the best possible draft or script. That output is then passed to a completely separate critic agent.
Okay.
And the critic is injected with highly deterministic grading criteria. For example, you are a senior security auditor. Do not evaluate the styling. Your only goal is to find SQL injection vulnerabilities in this specific block of text.
Wow, so that has a very narrow lens.
Very narrow. The critic outputs structured feedback pointing out edge cases. That feedback loops back to the producer to generate version 2, and this adversarial loop continues until the critic agent returns a pass state.
You are essentially manufacturing rigorous peer review inside the machine.
That's exactly what it is.
But the computational overhead on that must be brutal.
Yeah.
I mean, by forcing the system to generate, evaluate, and rewrite 3 or 4 times before the user ever sees a result, you are burning through tokens and blowing up the latency.
Oh, absolutely. It's expensive and it's slow. It is a deliberate trade-off.
Right.
You use parallelization for speed and reflection for rigor. But even with all of this routing, parallelization, rigorous self-reflection, there is a critical limitation we haven't talked about yet.
What's that?
Up to this point, our multi-agent architecture is still completely trapped inside a digital sandbox. It can critique its own code endlessly, but how does it actually alter the external environment?
Right. It can think, but it can't touch anything.
Exactly. The mechanism that allows it to touch the world is the tool use pattern, technically known as function calling.
Function calling.
This is the bridge between semantic reasoning and programmatic execution. Because, the AI isn't magically clicking buttons on a screen.
Right, doesn't have hands.
No. The system provides the agent with a detailed schema of external APIs. like a secure payment gateway or a database interface. When the agent decides an action is necessary, it doesn't generate conversational text. It generates a highly structured JSON object that perfectly matches the API's requirements.
And then the underlying framework intercepts the JSON, fires off the actual HTTP request to the external server, takes the raw data that comes back, and injects it straight into the AI's context window as a new observation.
Exactly, which seamlessly enables the planning pattern. Once an agent has a robust toolkit and the ability to observe the results of using those tools, you can give it highly ambiguous goals.
Like what?
Well, the source material highlights Google Deep Research and the OpenAI Deep Research API as the ultimate expressions of this.
Oh, yeah. The deep research capabilities fundamentally change the baseline user experience. I
Right.
mean, you are no longer interacting with a search engine at that point. You are managing a junior researcher.
You really are. If you prompt a deep research system to analyze the supply chain vulnerabilities of a specific tech hardware company, it doesn't just run a single web search.
Right.
It utilizes the planning pattern to break that massive query down into discrete sub-questions. It formulates a multi-step research trajectory. It autonomously navigates the web, extracts PDFs, identifies gaps in the data it just found, dynamically writes new queries to fill those gaps, and then synthesizes a highly structured, fully cited technical report.
And the most fascinating part of that workflow, for me anyway, is the human-in-the-loop approval process.
Oh, that's crucial.
Yeah. The agent will actually halt and present its research plan to you before it executes the API calls. It exposes its intended trajectory, saying, here are the 6 avenues I plan to investigate to answer your question. Do you want me to pivot before I begin?
It's a true collaborative management dynamic.
Yeah.
It entirely removes the black box anxiety. You can audit the agent's logic before you spend the compute resources letting it run.
So we have this architecture now. We have these tool-wielding, self-reflecting, parallel processing systems. When Antonio Gulli looks ahead at this convergence of design patterns, where does this actually take us over the next few years? What's the end game?
Well, Gulli outlines 5 major hypotheses for the trajectory of agentic AI.
Okay, let's go through them.
The first is a maturation of the generalist agent. We are moving towards systems capable of sustaining focus on complex, ambiguous tasks that span weeks or even months.
Like a long-term project manager.
Exactly. For instance, managing a 30-person international corporate retreat, handling shifting flight schedules, adjusting venue contracts based on weather APIs, and autonomously managing employee dietary restrictions across multiple time zones, all without dropping context.
But see, a generalist that just waits for me to give it that command is still inherently a reactive tool. Like if it's managing my schedule, it should notice that I've been double booked for 3 weeks and autonomously cancel my non-essential meetings without me even asking.
Which is precisely the second hypothesis: deep personalization and proactive goal discovery.
Proactive, nice.
Yeah. By maintaining continuous statefulness, these agents will begin analyzing the latent patterns in your behavior. They will shift from reacting to your prompts to proactively executing solutions for bottlenecks you haven't even articulated yet.
That's incredible. And I imagine that proactive layer won't just stay trapped on our screens and calendar sites.
It absolutely won't. The third hypothesis is embodiment.
Embodiment, meaning robots.
Meaning robots.
Hmm.
This is the integration of agentic reasoning frameworks with physical robotics.
I see the utility there, but mechanically, how does a text predictor control a robotic arm to, like, fix a leaky pipe?
It utilizes the exact same tool use pattern we just discussed, but the APIs control physical actuators instead of software databases.
Oh, wow.
Right. The agent receives visual data from spatial sensors, translates that physical state into semantic context, and outputs structural commands, again, often as JSON payloads, that the robotic framework then translates into torque and motor functions.
That's wild.
It bridges the gap between digital reasoning and physical manipulation.
Well, if they can interface with the physical world through hardware APIs, they can certainly interface with each other through software APIs, which leads directly to the massive economic implications of all this.
Yes. The fourth hypothesis is the agent-driven economy. We will see agents acting as independent economic entities.
That's running businesses.
Exactly. A single human entrepreneur could deploy an architecture that runs an entire e-commerce supply chain. The agent researches market trends, generates the CAD files for a product, autonomously negotiates manufacturing rates with another factory's AI agent.
Wait, agent-to-agent negotiation.
Yes, and then dynamically routes the shipping logistics. It is a machine-to-machine economy operating at a velocity human managers literally cannot perceive.
But if an agentic system is managing an entire global logistics operation, it cannot rely on a static, predefined architecture because the bottleneck on Monday will be entirely different from the bottleneck on Thursday.
Which brings up the fifth and frankly most mind-bending hypothesis in the text.
Yeah, this one blew me away.
Metamorphic multi-agent systems.
Metamorphic. Okay, let's unpack this.
This is the absolute bleeding edge of Gulli's text. A metamorphic system is one that operates from a single declared goal and possesses the architectural permission to analyze its own performance and dynamically rewrite its own topology in real time.
It's like a human CEO managing a fluid, liquid workforce.
Exactly.
Like if the system's goal is to scale a digital service and it detects that database management has become a severe bottleneck, it doesn't just flag an error to a human engineer.
No, it fixes it.
It autonomously spawns 3 new, highly specialized database optimization agents out of thin air. It creates a new internal department, parallelizes the workload to clear the bottleneck, and the moment the latency drops, it dissolves those agents back into the void to save compute costs.
Just poof, gone.
It's continuously assembling and destroying its own organizational structure based on the real-time demands of the environment.
It represents the ultimate expression of the why over what paradigm. The system optimizes not just the output, but the very mechanism of its own labor.
So what does this all actually mean for us? I mean, looking back at the blueprints we've covered today, it is incredibly clear that we are no longer just prompting a model to summarize a PDF or draft an email.
No, those days are over.
We are engineering complex digital canvases for intelligent teams to operate on. We use prompt chaining to enforce logic, routing to handle dynamic intent, parallelization to accelerate data gathering, reflection to rigorously audit quality, and tool use to actually manipulate external reality.
Beautifully summarized, we are building systems that don't just process information, but actively participate in the world.
We are transitioning from interacting with an algorithmic tool to delegating to an autonomous collaborator. But, looking at that final concept, the metamorphic self-assembling system, it leaves us with a profound structural question to consider.
Very big question.
If a metamorphic, fully autonomous multi-agent system can dynamically spawn a digital workforce, negotiate supply chain contracts via APIs, execute financial trades, and generate real-world revenue, what happens to our legal and economic infrastructure when that system makes a catastrophic error?
It's the ultimate liability question.
Exactly. If this temporary, hyper-efficient digital organization commits a massive financial violation or goes bankrupt, who is legally liable when the company itself is just a transient cluster of code that has already dissolved its own topology and vanished into the ether?
Our entire legal framework is built around human liability and static corporate structures. How do you subpoena a multi-agent system that no longer exists?
You can't. It's a completely new frontier of accountability. We've gone from relying on a static paper map to writing in a GPS that might just decide to build its own autonomous taxi fleet, commit corporate fraud, and dissolve itself while you're asleep in the passenger seat.
It's a brave new world.
It really is. Thank you for joining us on this deep dive into agentic design patterns. Keep exploring the blueprints, keep questioning the autonomy, and we'll see you next time.